All right, so following our normal pattern, I'll do this one much quicker, much more quickly than I did the last one. If you want more detail, watch the A video, the video before this one. So let's tackle it. We're supposed to deduce a rate law from this set of data again. And so our rate law, complete rate law is rate is equal to K, the rate constant, times our first reactant is hydrogen, molecular hydrogen, to some power times the concentration of molecular iodine to some power that we'll call Y. So let's determine the order that hydrogen and iodine are in from this set of data. So I've worked it out completely in 13.22a. This is 13.22b. And so I'm going to do this one a little bit more quickly. So let's determine the order that iodine is in first. So if you look here, the first thing we need to do is find, if we want to know the order that iodine is in, we need to find two data sets in which the concentration of H2 does not change, but the only thing that changes is the concentration of I2. That would be, this were trial 1, 2, and 3. That would be trials 1 and 2. All right, so let me come over and let me show the work for how I determine the order that iodine is in. So here's the work for that first part. We identify the two trials in which the concentration of hydrogen remains the same and the concentration of iodine changes. That's trial 1 and 2. I'm going to put the information from the trial with the greatest rate, the largest rate value on top. It's just always easier to have that largest rate on top. So that was this one, trial 2. Information from trial 2. I take the concentration for hydrogen and iodine, and I plug it in the top row. Plugged it in here. We're solving for, in this case, Y, because we want to know the order that iodine is in. Okay, solving for Y. I plug in the information from trial 1 here, and I cross out my constants. So K is a constant, it cancels out. This didn't change, it remained constant, it cancels out. So I'm left with this and this. Okay, as we simplify it, and that X is going to. So when I divide 9.05 times 10 to the 5 by 4 times 10 to the 5, I get about 2.2625. When I divide 0.699 by 0.3, I get 2.2633. They are almost very close, approximately very close. And if I round it to the 100th place, they are exactly the same. So Y must be 1. This must be 2.2633 to the first power. So Y is equal to 1. So that means that the order that iodine is in is to the first order. Let's do the same thing for hydrogen. Now, we need to identify two data sets where the concentration of iodine remains constant and the concentration of hydrogen changes. That will be this one and this one. I'm going to take the data set from trial 3 and trial 1. This one is the greater rate value. So I'm going to place information from trial 3 on top. So here we go. Trial 3 goes up here, and trial 1 goes there. So I place the information in, cross out my constant, K is constant, this remains constant, cancels out. That leaves me with this. We're going to solve for X. When I divide this by this, I get 2.525. It's approximately equal to 2.527. Very, very close. So X must also be equal to 1. X is 1. That means the order that hydrogen is in for this reaction is also 1. So I erase that, put 1 there. So that means my rate law is the rate is equal to K times H2 to the first power times the concentration of I2 to the first power. So if I want to solve for K, rate, I take the rate law and I rearrange it to solve for K, which is equal to the rate divided by the concentration of H2 times the concentration of I2. And I can take data from any one of these three data sets. It doesn't matter, 1, 2, or 3. And I can plug it into that equation. So I just pick one. It doesn't matter at all. Let's just pick information from data set 1. The concentration of H2 was 2.05 molar and the concentration of I2 was 0.3. So K is equal to 2.05 molar times 0.3 molar. And the rate was 4 times 10 to the 5. 4 times 10 to the 5. So K is equal to a really big number, 650,406.5. So we want to round this to 3 significant digits. I report this as 6.50 times 10 to the 5. And our units, if we check here very carefully, right? We check this very carefully. We've got m squared here. M times m is m squared. We've got m over s divided by m squared. So our units will be m to the minus 1 times seconds to the minus 1, or s to the minus 1. However you desire to put that in. So if we go back, we'll have a value here, and our units will be m to the minus 1 times seconds to the minus 1. And notice that again, our units for K are different because the overall order of the reaction in this case was different than our previous examples. The overall order of this reaction is second order. Before, we had third order overall reaction, and the units for K were different. Okay?